Kimi K3 scales to a whopping 2.8 trillion parameters. This new model shows strong performance across long-horizon coding, knowledge work, and reasoning benchmarks, making it competitive with leading closed-source models. Let's explore the architecture that makes this possible. Like any transformer-based model, Kimi K3 processes a sequence of token embeddings with a stack of attention and feed-forward layers. Its architecture scales information flow across sequence lengths, network depths, and model widths. Along the sequence dimension, it combines multi-head latent attention and Kimi delta attention in a 1:3 ratio. Along the network depth dimension, it replaces residual connections with attention residuals, allowing modules to access embeddings and prior blocks directly beyond conventional residual paths. We covered these topics in our previous videos. This video is about scaling the model widths. Width is the interesting one. It is the only axis where you can add parameters without increasing the computational cost per token. The feed-forward network first maps its input to a hidden layer, which is then projected to the output layer. And this is where most of a transformer block's parameters live. Between these transformations, a nonlinear activation function is applied to each dimension independently, enabling the model to learn complex patterns. A straightforward way to scale the model width, and thus its capability, is to increase the dimension of the hidden layers in the feed-forward network. But all these weights are used by every single token, so this slows down both training and inference, and it demands more memory. This is where mixture of experts comes in. The key insight here is that not every token benefits from the same transformation. Yet a standard dense layer applies the same weights uniformly to all tokens. Effectively, we partition a large feed-forward network into smaller, more specialized expert networks. For each token, we activate only a sparse subset, here 2 of the 8. As a result, we obtain a much larger and more expressive network, without increasing the computation each token costs. But how do we decide which experts to activate for each token? A common approach is to use a trainable router network to predict one score for each expert. Here the router network predicts a vector of 8 logits. Applying a softmax to these scores converts them into a probability distribution over the experts. We select the top 2 experts with the highest probabilities. Next, we send the input token embedding to the selected experts for processing. Each selected expert processes the input independently and generates its own output. This produces the final output of the mixture of experts layer. Now watch the router work. Different token, different 2 experts. The pool stays the same, only the choice changes. In short, the final output is a weighted sum over the selected experts, where each expert's output is scaled by its router probability. This is the mixture of experts layer. But here we only have 8 experts to choose from. Scaling the number of experts unlocks even greater performance gain. Such a design is called fine-grained experts. In Kimi K3, the pool is 896 experts and only 16 fire per token. As an illustration, the grid here is a scaled down 256 with 8 lighting up. In addition to specialized experts selected by the router, the model includes 2 shared experts that are always active. The shared experts cover broad common knowledge for all tokens. Specialized experts focus on specific domains. Increasing both the number of experts and the number of active experts per token expands the range of possible expert specializations. However, each routed expert receives the entire d-dimensional embedding for each routed token. Since the experts are distributed across many GPUs, activating more experts for each token results in a significant communication overhead. For example, each token embedding may have 7,168 dimensions, and this high-dimensional vector must be transmitted to every selected expert during routing. While this approach works well for the shared experts, it becomes problematic as we expand the number of activated experts. To make this expansion affordable, we compress the token embedding into a latent vector using a linear projection matrix W down. The latent vector is half the width, 3,584 instead of 7,168. And notice there is one W down, not one per expert. The token is compressed once, and the same small vector goes out to all the routed experts. The specialized routed experts thus operate in a compact latent space. After aggregating the expert outputs using the router probabilities, we project the result back to the original d-dimensional space by a second matrix, W up. The final output is the sum of the outputs from the shared experts and specialized routed experts. This is latent mixture of experts. Latent MoE cuts routed parameters and communication, so the model can spend what it saves on more experts and more of them active per token. Better accuracy at a similar inference cost. But this design faces challenges when scaling up the sparsity. For every selected expert, the token now runs through a chain of matrix multiplications, down through W down through the expert's own feed-forward network, and backups through W up. This chaining of matrix multiplications can make training unstable. Each step can amplify values, compounding until they exceed what low-precision number formats can hold and trigger overflow. Kimi K3 addresses this instability in two ways. First, Kimi K3 inserts a normalization layer between the expert aggregation and the up projection step. RMSNorm stabilizes the routed branch by normalizing the aggregated expert output to a consistent size before it is merged with the shared expert branch. Because the expert sum can vary widely depending on routing, this normalization ensures the up projection always receives inputs of uniform scale. This simple change not only stabilizes training, but also leads to improved validation loss and better performance on downstream benchmarks. Second, we look into the design of each shared or routed expert. As discussed earlier, each expert is just a small two-layer MLP. Commonly used element-wise activation functions include swish and GLU. One way to understand these activations is through the lens of content and gating. Here, the activation is computed as the element-wise multiplication of two components for each input value z. The first is the content function, which passes the input through unchange. The second is the gating function, which controls how much of the content passes through, essentially an adaptive filter. Using the sigmoid function as our gate, we get the swish activation function, also known as SiTU-GLU, sigmoid linear unit. Using the cumulative distribution function of a standard normal distribution yields the GLU activation, Gaussian error linear unit. Swish and GLU embody the same principle. Instead of a hard cutoff at 0, each value gets to control smoothly how much of itself passes through. Building upon the content and gate interpretation, we can generalize the framework to enable more flexible ways of extracting content and designing gating mechanisms. For content, we apply a dedicated weight matrix WV to the input Z, producing a learned content vector. Similarly, we can compute the gate vector using a learned matrix WG, followed by applying the gating function. A learned WG matrix lets the gate depend on arbitrary linear combinations of the input, not just element-wise values. This gives the model greater flexibility in controlling which features to pass or suppress, improving its expressiveness and learning capacity. The activation vector A equals the element-wise product of the content and gate vectors. A more general form of these linear transformations also includes bias vectors BV for content and BG for gate. However, in practice, modern models frequently omit these bias terms to improve training stability and computational efficiency. Recall that the pre-activation vector Z isn't the original token itself. It's the result of passing the input token X through the XBurst first layer, W1, which expands its dimensionality. We can thus express both the content and gate vectors in terms of the input vector X. Both the content and gate matrices are applied right after the XBurst first matrix, W1. Thanks to the associative property of matrix multiplication, we can effectively absorb W1 into the content and gate matrix, treating each as a single unified linear transformation. This gives us a family of gated linear unit activations that differ only in the choice of gating function. But here comes the problem. Look at the two things being multiplied. The multiplicative factors are unbounded. And in low precision, a single large product is enough to overflow. Let's follow a single dimension and plot what comes out as Z grows. When Z is large, glue grows in step with it. But SiTU-GLU grows like Z squared and leaves the frame entirely. What we need is approximately linear near the origin and bounded at large magnitude. The soft cap function satisfies this property. For small inputs, tan edge is almost the identity, so this just hands the input value straight back. The cap does nothing at all until the values get large. We can adjust the bound by setting the value of beta. Now let's revisit the SiTU-GLU activation. Here is the content branch, and here is the gate branch. Both multiplicative factors in SiTU-GLU are unbounded because of these linear terms. Now you probably can see where we are going. We apply the soft cap function to the linear terms in both branches. Each branch gets its own cap, beta 1 on the gate, beta 2 on the value. So the product can never exceed beta 1 times beta 2. In Kimi K3, that is 4 on the gate and 25 on the value. The activation can never exceed 100 no matter what comes in. This limits excessive activation values, while still preserving SiTU-GLU's distinctive local behavior and its smooth, nearly linear response for positive inputs. This is called sigmoid 10-unit glue. For large input values, this variant produces bounded activation values. At the same time, for small input values near 0, the output closely follows SiTU-GLU. So a normalized latent MoE and a bounded activation inside every expert. With these two techniques, the activation can no longer blow up. But there is another kind of instability. Training highly sparse, fine-grained experts is very challenging. At the start of training, all the weights in these experts are initialized randomly. This means that all these networks are equally bad. Now imagine the router assigns the first few tokens to the first two experts. As these two experts are updated more frequently than others, they start to perform better. This creates a self-reinforcing behavior where the router becomes increasingly inclined to route most tokens to the first two experts. Over the course of training, the remaining experts may rarely, if ever, be activated, causing them to become effectively dead. This brings us to the load balancing problem. Put simply, our objective is to ensure that token processing is distributed as evenly as possible across all experts. One popular approach adds an auxiliary loss, computed on the router's own probabilities, that penalizes uneven allocation. However, incorporating these auxiliary losses introduces a trade-off between model performance and load balance. The catch is that this loss pulls on the same weights as the language modeling loss. The model is now spending capacity on being balanced. DeepSeek V3 avoids that trade-off with a simple trick. Here, the DeepSeek V33 router simply uses a sigmoid on each expert's logit. A sigmoid scores each expert on its own, instead of a softmax that forces the 8 scores to compete for a fixed budget. This independence lets us adjust the bias for each expert individually without affecting the others. Suppose this router is slightly biased towards selecting the first 2 experts. For example, in a batch of tokens, it is unsurprising that the first 2 experts receive significantly more tokens than the others. 24 tokens in, and 2 experts have taken almost everything. To address this imbalance, we add a small dynamic bias for each expert, adjusting it based on whether that expert has received more or fewer tokens than the average. This gives us adjusted scores to determine the top K routing. Let's try another batch of tokens. This simple bias adjustment increased the likelihood of tokens being routed to a broader range of experts. However, the first 2 experts still dominate routing assignments. So let's update the bias again. We start to see more balanced expert routing assignments. Let's try adjusting the bias again. By dynamically adjusting the bias for overloaded or underloaded experts, we keep balanced expert load while achieving better performance. Note that the bias adjustment was only used for determining top K routing. It changed which experts win the top 2, not the scores themselves. The final output still uses the original sigmoid scores as weights for combining expert outputs. This is the auxiliary loss-free load balancing strategy. But this was 8 experts. Kimi K3 has 896 of them per layer. Maintaining balanced loads becomes challenging. Incrementally adjusting the bias can also be slow to achieve balanced expert utilization. The update only knows the sign of the error: too many tokens or too few. So a bias that is wildly off moves no faster than one that is nearly right. The process is sensitive to the hyperparameter that determines how quickly the biases respond to uneven expert allocation. Instead of gradually nudging each expert's bias toward the right value, can we just compute where it needs to be? Let's work through an example. Consider a scenario with 8 experts in the pool, where the router handles a batch of 16 tokens. The router produces routing scores across the experts. We can already see 2 columns standing out. Suppose we use top 2 routing. We can see that the first 2 experts are frequently selected. This causes the load imbalance problem. If we take the router scores for each token and sort the values, we get the threshold value alpha. For top 2 routing, we pick alpha as the 3rd highest router score. So alpha is a bar. An expert wins this token only if its score clears it. With the token bar, we can compute the margin. That is how far each router score is above or below the token bar. This is the crucial step that levels the playing field between columns. Some tokens consistently assign higher scores across all experts, but by subtracting each token's own threshold, we remove those baseline differences. Now each column reflects only meaningful variations, making them directly comparable. We can now decide how to select the best bias value for each expert. Let's first compute the target load for each expert. It's the number of tokens times k divided by the number of experts. In our example, we have 16 tokens. Each token is routed to 2 of the 8 experts in the pool. So, in the ideal case, each expert should receive 4 tokens. Now, we take a closer look at the margins across the tokens for the first expert. Sort them high to low and cut after 4, because 4 is the load this expert should have. The block sitting right at the cut, the 5th one down, has a margin of 0.27. This suggests that we should adjust the bias for this expert by subtracting 0.27 from the score. For this batch, that's an exact match. By definition, the 5th largest margin is the value that sits just below the top 4. Repeat this process for all 8 experts. Sort their margins, make the same cut, and assemble the complete bias vector. When the next batch of tokens arrives, with their own router scores and token bars. We apply the bias vector to these new scores. Then we route the tokens using the same top K rule as before. This gives us a much more balanced load. 6 experts are exactly on target, and the other 2 are off by 1. The new load is close to ideal. This is called Quantile Balancing. Quantile Balancing computes the bias directly from the routing score distribution, rather than searching for it through gradual or heuristic adjustments. No step size, no tuning, no weighting. This targeted approach yields faster and more stable convergence to balanced utilization, ensuring efficiency as the number of experts scales. In summary, LatentMoE makes the experts efficient. 3 core techniques: RMSNorm on the routed branch, sigmoid tanh unit glue within each expert, and quantile balancing on the router work together to stabilize training. This synergy enables Kimi K3 to reliably scale up to 2.8 trillion parameters. Thanks for watching, and I'll see you next time.